Today, we're going to talk about direct current generators. A direct current generator converts mechanical energy into electrical energy. The operating principle of electromagnetic generators was discovered in the year 1831 by Michael Faraday, and the first direct current generator emerged in the 1860s. Till today, direct current generators are still currently being used.
So, the first point we will talk about the working principle of DC generator, which is relating to Faraday's laws and Lenz's law. Now we will first talk about Faraday's law. Faraday's law states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. And also, we have our Lenz's law. Lenz's law states that induced current flows in such a direction which is opposed the change or motion causing it. Here is an example of how to determine the direction of current using Lenz's law. Now we have a square loop of conductor over here, and the vectors represent the magnetic field. When we increase the magnetic flux, the magnetic field will become stronger, and so the vector will become larger. According to Faraday's law, this change in magnetic field will produce an induced current in the loop. And to determine the direction of the current, we will be needing Lenz's law. Remember that Lenz's law states that the magnetic field produced by the induced current will oppose the change in magnetic field. So there are two scenarios as to what the direction will flow in. The first one is clockwise, and the second one is counterclockwise. Let's talk about the counterclockwise first. Using right hand grip rule, you can see that our fingers are wrapped around like that. So, a magnetic field going upwards is produced. And this will be additive to the change in magnetic flux. This also will increase the currents again. So, in conclusion, the current will not flow in counterclockwise in this case, as it does not obey to Lenz's law. Now, let's talk about clockwise directions. By using the right hand grip rule again, we can know that the magnetic field produced by the induced current will go downwards. This will decrease the change in flux. This is an accordance to Lenz's law, as the magnetic field produced by the induced current opposes the change in magnetic flux. So, this is the correct one. So, this is a simple DC generator, consists of a coil of insulated copper wire A, B, C, and D. The coil is placed between the two poles of a strong magnet. The two ends of the coil are connected to the two halves of the spring ring E and F. These two spring rings are also called commutator, and two carbon brushes pressed against the two half rings lightly. X and Y is the two carbon brush, and the current is taken out through the brush by X and Y. Finally, we will talk about the working principle of DC generator. Let the coil A, B, C, and D be initially in the horizontal position and be rotated anticlockwise. When the coil is rotated anticlockwise, the arm AB moves downwards and the arm CD moves upwards. The coil during this motion cuts the magnetic line of force and an induced current is produced in the coil. According to Fleming's right-hand rules, during the downward motion of arm AB, the current flows from B to A in arm AB and from D to C in arm CD. By applying our Fleming right-hand rule, our thumb is represent the motion and the force, and the forefinger are represent the direction of the magnetic field. The second finger is represent the direction of the current. So we can know that the direction of the current is flow from B to A and from D to C. The current so produced is taken out through the two half split ring and the carbon brush. So, after the half rotations, the arm of the coil interchange their positions. The arm AB comes to the right and arm CD comes to the left. Then the arm CD start moving downward and arm AB start moving upwards. During this half rotation, the induced current flows from C to D in arm CD and flows from A to B in arm AB. The two half split rings R1 and R2 rotate with the coil and touch the two carbon brush B1 and B2 one by one. As a result, each carbon brush continues to have the same polarity. The brush B2 always remain positive terminal, and the brush B1 remain negative terminal. The current so produced is called direct current.
After learning the working principle of DC generator by relating to Faraday's law and Lenz's law, I'm going to be talking about the relationship between flux versus time graph and EMF versus time graph. In this picture, we get to see the positions of the coil, and we also get to see the flux against time graph. I'll put it as graph number 1. And we also see the EMF against time graph, which I'll put it as graph number 2. Okay, so when the coil is in a vertical position, as you see in diagram A1 over here, with LK on top, size LK on top, and MN below, we get to see that the flux is at maximum here. I'll just put it as number 1. And we get to see that the EMF is 0. So why is this? When the coil is in a vertical position, the tangential force is perpendicular to the flux. Hence, there is no flux cutting, and so the flux is maximum while the EMF is 0. And this is in accordance to Faraday's law. Faraday's law states that when there is flux cutting, or when the coil is perpendicular to the flux, the EMF is maximum. Okay, so when we look at diagram number 2, we see that the coil is flat. The coil is horizontal. So when the coil is horizontal, there is no flux. And when the coil is horizontal, the perpendicular motion of the coil is, the tangential motion of the coil is perpendicular to the magnetic flux. And when this happens, the EMF is maximum. As you can see here, I'll put it as number 2 again, which refers to diagram A2. As for the direction of the current, we can use Fleming's right-hand rule to determine. And so, at diagram 3, we get to see that Mn is above while Lk is below. It's exactly the same as diagram number 1, except with sides Mn above and sides Lk below. When this happens, the tangential motion is parallel to the flux. Hence, there is no cutting of flux, and so flux is maximum. Although it's maximum, we actually see the graph below 0. This is because of the sides that are different, the sides that are opposite. Okay, so I'll just put this as number 3. While the EMF, once again, is 0. And so the cycle repeats itself. And yeah.
So now we're talking about the mathematical equations related to the EMF of DC generator. Let P equals to the number of poles of the generator. Phi is the flux produced by each pole in Weber. N is the speed of armature in revolutions per minute. Z is the total number of armature conductors. And A is the number of parallel paths in the armature. Now we know that EMF gets induced in the conductor of the DC generator according to Faraday's law. Hence, the average value of the EMF induced in each armature will be the rate of cutting of flux. Therefore, EMF will be the change in flux over the change in type. Now, in one revolution of the conductor will cut the total flux produced by all the poles. That's why the total flux produced by all the poles will be phi, which is the flux produced by each pole in Weber, times P, which is the number of poles. Now, moving on, the speed of the armature is N, but that is in revolutions per minute. So the time taken in seconds will be 60 over N. Now when we put that together, we'll get the EMF is the total flux, which is phi times P over the time, which is 60 over N, and we will get phi P N over 60. But this is the EMF induced in one conductor. Suppose there are Z number of conductors in a generator, arranged in a manner that all parallel paths are always in series. And when Z is the total number of armature conductors and A is the number of parallel paths, then Z over A will be the number of conductors connected in series. Induced EMF in each path is the same across the line. Therefore, the induced EMF of a DC generator will be the EMF of one conductor times the number of conductors connected in series. So the EMF will be, from what we got from just now, phi Pn over 60 times the number of conductors connected in series, which is Z over A. And we will get phi P and Z over 68. So this is the EMF equation of a DC generator. But there are two types of winding for a DC generator. One is the lap type and the other one is the wave type. And in the lap type, the number of parallel paths A will be equal to the number of poles P. So when we simplify the equation 5pnz over 60a, simplify it, we will get 5nz over 60. And this is the equation for lap type of winding. For the wave type of winding, we know that the conductors are connected to two parallel paths irrespective of the number of poles of the generator. Hence, the number of parallel paths A will be 2. And we will get 5pnz over 60 times 2. And that will be 5pnz over 120.
EMF in a DC generator can be produced by using two or more coils. As shown in the diagram, the commutator must be divided into 4 parts since there are 4 coil ends. The coil is rotated in a clockwise direction from the position shown. The voltage induced in coil X decreases from the next 90 degrees of rotation from maximum to 0. The voltage induced in the coil Y increases from 0 to maximum at the same time. Since there are 4 segments in the commutator, a new segment passes each brush every 180 degrees of rotation. This allows the brush to switch from the coil X to coil Y at the instant the voltage in the two coils are equal. The brush remains in contact with the coil Y as its induced voltage increases to maximum level B, which is in the graph. It then decreases to level A 90 degrees later. At this point, the brush will contact the coil X again. Since there are now 4 commutator segments in the commutator and only 2 brushes, the voltage cannot fall any lower than at point A. Therefore, the ripple is limited to rise and fall between point A and point B on the graph. EMF produced by 2 or more coil DC generator will be higher than the single coil DC generator. This can be proven by the equation of Faraday's law of electromagnetic induction, which states that EMF can be found by using the formula final magnetic flux minus initial magnetic flux over change in time multiplied by the number of turns in a coil. So, as per this equation, when number of turns in a coil increases, induced EMF will also increase.
Throughout the years, there have been plenty of modifications of DC generators, and here are a couple. The next slide will be showing you a modification example. When the voltage is applied to the field windings of a DC generator, current flows through the windings and sets up a steady magnetic field. This is called field excitation. The excitation voltage can be produced by the generator itself, or it can be supplied by an outside source, such as a battery. A generator that supplies its own field excitation is called self-excited generator. Self-excited is possible only if the field pole pieces have retained a slight amount of pattern or permanent magnetism, called residual magnetism. When the generator starts rotating, the weak residual magnetism causes a small voltage to be generated in the armature. This small voltage is applied to the field coils, causes a small field current. Although small, this field current strengthens the magnetic field and allows the armature to generate a higher voltage. The higher voltage increases the field strength and so on. This process continues until the output voltage reaches the rated output of the generator. Another example of a modified generator is a practical generator. The simple loop generator has been considered in detail merely to bring out the basic principle underlying construction and working of an actual generator. The outer frame or yoke serves double purpose.
It provides mechanical support for the poles and acts as a protecting cover for the whole machine. It also carries the magnetic flux produced by the poles. In small generators where cheapness rather than weight is the main consideration, yokes are made of cast iron, but for large machines usually cast steel or rolled steel is employed. The modern process of forming the yoke consists of rolling a steel slab around a cylindrical mandrel and then welding it at the bottom. The feet and the terminal box and such as those are welded to frame afterwards. Such yokes possess sufficient mechanical strength and have high permeability.